Today, I'm going to be talking about the complete sufficient statistic. And my name is Carla Aguila Salamanca. To start, I'm going to give a little introduction. And well, for many parametric problems, it is possible to summarize all the information about data contained in a random variable x by a function. And this function is equal to t, that is equal to t of x, which is called a sufficient statistic. This is the definition of a sufficient statistic. And well, the completeness is another concept and it's a technical property of a sufficient statistic. And this sufficient statistic, which is also complete, must be minimal sufficient. The implication is that any reasonable estimator of theta will be a function of t of x. It's important to say that we always not may have the complete information about the parameter theta. The definition of a complete sufficient statistic is that a statistic t is called complete if the expected value of the function j that depends on t is equal to 0 for all theta, and some function g implies that p of the function g is equal to 0, and this depends on theta is equal to 1 for all values of theta. This use of the word complete is analogous to calling a set of vectors from v1, v2 to vn complete if they span the whole space. That is, any v can be written as a linear combination of the v equal to the sum of all aj multiplied by bj of these vectors. Then we have an example of this complete sufficient statistic. And well, we are going to be discussing the coin flip example, an example that is very common in this type of examples. And well, we claim that t equal to x1 to xn, and this is a complete statistic. To check this, we suppose that the expected value of the function g is equal to the sum of this function multiplied by the probability of this statistic is equal to a value t, and this is equal to the sum from the t equal to 0 to n to the combination of n and t multiplied by the value of theta to the power of t times 1 minus theta raised to the power of n minus t for the function g equal to 0. We observe that this is a polynomial in theta, which can only be identically equal to 0 on an interval if all coefficients are 0. Now that we have the expected value of g, we have that this is equal to g evaluated in 0 multiplied by 1 minus theta. And well, we have this formula, so it already follows that g of 0 is 0, because otherwise we will get a non-zero constant term. But then we have the sum from t equal to 1 to n to the combination of n on t times theta to the power of t times 1 minus theta to the power of n minus t to the function g, and this is equal to 0. Now we can divide through by theta, and then this repeats this argument to conclude that g of 1 is 0. Now, an example 2, we suppose from the previous example that we restrict the value of theta to 3 values that are 0, 1/2 and 1. And we ask ourselves if this is still complete. The geometric interpretation discussed shows that the answer is no. For random samples of size that n is greater or equal to 3. Indeed, we only have 3 vectors corresponding to the 3 possible values of theta, but these vectors lie in an dimensional space because t varies over 0, 1 to n, so they cannot possibly span the whole space. And well, this complete sufficient statistic also have many misinterpretation because we need another theorem to understand fully this topic, and this complete definition lead us to a possible misleadings where we have to use another theorems to apply in this type of definitions. And here are the references.